So this is the first video on one of my favorite topics in physics, what is called elementary particles. I love this topic because it asks some of the big questions, or I guess you could say small question, which is how small can matter really go? You know, in the 1800s we had Dalton's theory and we thought that atoms were as small as they get. And then by the early 1900s, about the 1930s, we figured out that we could break atoms apart into three subatomic particles, protons, neutrons, and electrons. We also quickly found another particle called the positron, which I'll talk more about later. And we knew about photons. I don't put an exact date here because different photons were discovered at different times, like the gamma particle, X-rays, and radio waves, and these things were discovered at different times. So the question is, how far can we go? Are these guys now elementary, or what we might call fundamental particles? And the answer, as you probably know, is, well, yes and no. The electron we think is fundamental. The proton and neutron we think we can break up into, actually we know we can break up into smaller things. And can we break those things up into smaller things? Well, that we're not sure about. We think probably not, but we won't really know unless we build ever larger and more powerful particle accelerators to try to figure that out. So the reason we need particle accelerators is some of these other particles that we know about today don't just show up in your average desktop lab experiments. You need lots of energy, and then we can kind of spontaneously produce them through collisions. And we're going to use Einstein's famous equation. I'm not going to derive it here. It's derived in our unit on relativity, but we're going to go ahead and use it here anyway. So this tells us that matter and energy are interchangeable. So if I want to create some new particles, what I can do is smash two particles together at really high energy, and some of that kinetic energy actually can get converted to mass and create new particles. And that's what's going on with these crazy pictures like on the side here. Alright, so as a simple example, let's say of just applying this equation to these types of interactions. Let's say we have a neutron and it decays to a proton plus an electron plus some extra energy. It actually gives off another particle here, but we haven't talked about that type of particle yet. So we can use E equals mc squared to figure out how much energy must be released in this reaction. Now before we jump into that calculation, I'll mention that particle physicists use some really weird units for mass. They use what are called mega electron volts per c squared. Yeah, what the heck is that thing? Well, an electron volt is an amount of energy, and then mega is just millions of electron volts. This is actually the amount of kinetic energy that an electron has if it gets accelerated through a potential of 1 volt, which we haven't covered. That's okay, we don't really need to understand all of that. Okay, so if this is a mass and we plug it in here for mass, we're going to get energy units, MeV, over c squared, and that's going to cancel with this c squared, so we're just going to be left with the energy units. So that's why they use these. They're weird, but they're actually pretty convenient when you're using E equals mc squared a lot, because this c squared goes away. And the reason to have mega electron volts, why that's useful, is in particle accelerators, usually you know the voltage with which you're accelerating your particles, so it's just a convenient way to measure the masses. If you're interested, 1 mega electron volt, I don't know that we're going to need this conversion, but it's 1.78 times 10 to the negative 30th kilograms. So a very small amount of mass is 1 mega electron volt. And mega electron volt per c squared. As I mentioned earlier, 1 mega electron volt is a unit of energy, and it's actually equal to 1.6 times 10 to the negative 13th joules. This is a unit conversion that we're going to need, so you might want to jot that sucker down in your notes. Okay, so coming back over here to this little expression, rather than plugging in the masses of these guys in kilograms, we can actually think of this as an energy equation. So we've got the mass of the neutron times c squared, which is essentially the energy initially present in the neutron, goes to the mass of a proton times c squared plus the mass of an electron times c squared plus some energy. And this is what we're going to solve for. We want to know how much energy is released when a neutron decays into a proton and an electron. And so you can look these up on a table, but I'm just going to give them to you right here. So the mass of a neutron is 939.57 MeV per c squared. Okay, weird number, but once you get used to it, it's not too bad. Okay, so that's just the mass, so that gets multiplied by the c squared still, and those go away, and so we just have that energy. Okay, and we're going to make this an equal sign because of conservation of energy. The energy we start out with over here has to equal the energy we end up with over here. The mass of a proton is 938.27 MeV per c squared, and I'm just going to leave the c squareds off because they cancel. The mass of the electron, as you probably already know, is much less, about 1,000 times less, no, 2,000 times less. Anyway, 0.511 MeV per c squared, and the c squareds cancel out. And then we can solve for the amount of energy given off in this decay. All we have to do is subtract these guys from this guy, and we end up with a bit of energy, 0.789 mega electron volts of energy. And as I mentioned earlier, this energy is in another particle, and it could be in the kinetic energies of these particles as they decay, if this was initially at rest and these guys went flying or something like that. Okay, let's look at a few different types of particle accelerators and briefly how they work. We're not going to go into details here because it involves a bit of electricity and magnetism, which we aren't covering. So one of the first types of particle accelerator was known as a cyclotron. A fun name, yes. And essentially, if you have some charged particle and you stick it in a gap between two, these are going to be metal with like channels in them, and you apply a voltage, that voltage is going to set up an electric field. Again, I know we haven't covered all this stuff, but essentially it's going to accelerate this charged particle, and it's going to fly this way. And then inside these parts here, you're going to have a magnetic field, and that magnetic field is going to bend the particle around, so it's like it goes flying this way and it curves it around that way. Then when it hits the gap, it accelerates again. Now in order for that to happen, this voltage had to swap. So this guy goes to positive and this guy goes to negative. So you have to have an alternating voltage here back and forth. So it flies this way, a magnetic field curves it around, then you switch back to the original voltage configuration, it flies that way. Anyway, it just keeps getting accelerated around and around and around, and eventually comes flying out at pretty high energies or high speeds, coming out this way. The nice thing about this configuration, and these are still used, these aren't used so much for research anymore, but there's plenty of medical equipment and stuff that still uses cyclotrons to get particles for medical imaging and things like that. The nice thing about this is you can have a constant magnetic field, and as this radius increases, you have a constant frequency here as well. So it's a pretty simple way to accelerate your particles. Some more sophisticated ways are what is called a synchrotron, and here you want a constant radius to your circle. So in order to do that, you have to increase your magnetic field as these things speed up. Also, as they get near the speed of light, you need to change the frequency of that applied voltage. Anyway, this is known as the Large Hadron Collider, kind of a famous particle accelerator, the largest one in the world. The diameter, not diameter, the circumference of this circle is like 26.5 kilometers, pretty big. This is on the border of Switzerland and France at a research facility known as CERN, the Centre Européen de Recherche Nucléaire. Anyway, this is a picture inside the tunnel here. There's the beam here, and there's some space in the tunnel here so people can work on the equipment. But this had a different accelerator inside the tunnel before called the LEP. And they dismantled that and built the new LHC, which went online a few years back and famously discovered the Higgs boson. And yeah, this here is showing the different detectors along the beam line that they crash the particles into to see what comes out. And you get beams going in opposite directions. So you get more energy if you collide two beams that are both moving at high speeds with each other rather than just one beam with like a stationary target. Anyway, these are called synchrotrons because of the varying frequency of the voltage you apply. It has to be synchronized with the movement of the particles. All right, one last type of accelerator we'll look at is called a linear accelerator, named probably as you can tell because it goes in a straight line rather than a circle. These can get pretty high speeds too, not as high as the synchrotrons. But this has its advantages. The synchrotrons lose a bunch of energy because charged particles, when they're accelerating, which they are when they're going in a circle, naturally radiate energy, whereas in this case they don't necessarily lose energy due to radiation. This is a famous one called the SLAC, which is the Stanford Linear Accelerator, and it's I think it's like 3 kilometers, about 2 miles long. So still a pretty big piece of scientific equipment. All right, moving on from accelerators. We're going to go back in time a little bit. It was in the 30s that Japanese scientist named Hideki Yukawa, Y-U-K-A-W-A, he proposed the idea that forces between objects were mediated by other particles being exchanged. And some people kind of consider this the beginning of particle physics. So before that we studied protons, neutrons, and electrons, and then we started getting into figuring out the fundamentals of how chemistry worked and all of that. But here, when we looked at the fundamental forces and how those were working on the most small level possible, this kind of kicked off the branch of physics known as particle physics. So some forces are attractive, like gravity and the electromagnetic force. If you have a positive and a negative charge, those are going to be attracted, right? Opposites attract. And some forces are repulsive, not gravity. Gravity we think is pretty much always attractive, well, unless you have dark energy and doing weird things. But in most situations, it's just attractive. But charges, if you have like charges, either two positives or two negatives, then those are going to repel each other. And so we're going to try to explain both of those things using this kind of crude pillow analogy. So for repulsive force, it's pretty straightforward. If this guy throws a pillow that way or shoots a particle that way, and this guy shoots a particle that way, even if he doesn't catch this guy's pillow, by throwing that pillow, by conservation of momentum, he is going to feel a force backwards, or he's going to be moving backwards. Okay, and then if he catches the particle from the other guy, then he moves backwards even more. So this, if you had a whole bunch of pillows in your back pocket and you kept throwing them at somebody else and they kept catching them and you caught the ones they were throwing at you, you would eventually move away from each other. They're wearing nice low friction roller blades here. Okay, and then we can kind of say you can have an attractive force if they're exchanging them by handing them off. So in that case, they'll end up pulling on the pillows a bit and pulling toward each other. What's actually going on the fundamental level, I don't know that anybody has a real intuitive understanding, but mathematically we can describe it and it works out well, and here's a rough analogy. It works okay. All right. So here is a diagram of just such an interaction. If we have a couple of electrons, so this is space over here. You can think of this as a position time diagram, but flipped from the way we usually use them in kinematics. So these guys are moving toward each other because they're moving along the spatial axis, if this is in meters or something. These guys are moving toward each other in time because time is going up. At this point in time, this electron emits a photon, and when it emits that photon, it gets pushed back because it threw something. And then this electron, a little bit later, receives that photon and it gets knocked back. And so the net result is the exchange of a single particle. These particles, we call them virtual particles. So these exchanges happen so quickly, you can never like intercept this particle halfway in between. It's just not possible. So anyway, you end up with a net result of a repulsive force, and in this case we say that the photon was the pillow. That is the particle that mediates this repulsive force. This is known as the electromagnetic force, and so we've got a photon that's doing the job. This picture here, by the way, is known as a Feynman diagram, named after Richard Feynman, pretty famous physicist for those who pay attention to physicists. He's dead now, but he did all kinds of cool things. Helped with Los Alamos, helped figure out why the Challenger exploded, and helped figure out part of quantum mechanics. Anyway, back to Yukawa. So Yukawa was the one who kind of first came up with this idea of particle exchanges, mediating forces. And they knew that there were forces holding the nucleus together in the middle of atoms. And so in that case, you've got protons and neutrons. And they figured that the interaction between protons and neutrons was some other particle that they called a meson. Okay? And they weren't really sure. This particle was proposed theoretically before it was discovered. But they knew something about the strong force. They knew how far it could reach, how far the particles could be apart and still influence each other. And so they were able to predict the mass of the exchange particle that must be mediating the strong nuclear force. And so I'm going to invoke a little thing called the uncertainty principle, which is another thing we didn't cover that we're going to look at when we do quantum mechanics. And there's different manifestations, so to speak, of the uncertainty principle. But one of them is that the uncertainty, and I'm not talking about delta here in our regular sense of final minus initial. I'm saying delta where I don't know if it's bigger or smaller. So the uncertainty, the amount of by which my energy can vary, and I don't really know exactly what my energy is, that amount multiplied by the uncertainty in the time has to be equal to or greater than, I'll just say approximately equal to, what's called Planck's constant divided by 2 pi. Planck's constant, by the way, I'll jot that down over here, is 6.6 times 10 to the negative 34th joule seconds, joules times seconds. Okay, so essentially what this is saying is the more I know about the energy, if I know that very precisely, that means my uncertainty in the energy goes down. I'm very certain of my energy. The more I know about the energy, the less I know about when the particle or the system had that energy. So my uncertainty in the time goes up if my uncertainty in the energy goes down, and vice versa. If I know exactly when it had some energy, then I don't know exactly what that energy is. So that's what this relationship is telling us. It's a fundamental property of quantum systems, that the more you know about certain quantities, the less you know about another quantity. Okay, so here we have this virtual particle that just gets created out of nowhere, which seems to violate conservation of energy. But we can use this uncertainty principle as kind of a fudge factor and say, well, if this is mass, and if mass is equivalent to energy by E equals mc squared, I can create a little bit of mass or a little bit of energy as long as it's less than my uncertainty, because it's basically, I don't know whether or not that energy was there to begin with, and if it might have been, then this particle might have been there. Okay, so we're going to say that the amount of our uncertainty is going to be equal to mc squared. Okay, now the the uncertainty in my time has got to be equal to or less than the time for this particle to travel from one particle to the other, the time for the exchange particle to travel, for the pillow to fly from one person to the other. Okay, and that time is going to be the distance between the two particles divided by, we're going to be kind of conservative here and say the speed of light. So that is the fastest it could go, so that's the minimum time it would take for some particle to go between the proton and the neutron. Okay, I'm just going to go ahead and set this as an equal sign because squiggly equal signs are harder to draw. So if we have this relationship here, and if I rearrange it, I get mc squared is equal to Planck's constant times c over 2 pi d. And we don't want to cancel out these c's because, as we saw earlier, when we plugged in a mass in MeV per c squared, then the c squareds cancel out anyway, so it's actually easier to leave that c squared in there and then plug in our masses in MeV per c squared. And then I've got my d over here. Okay, so we knew something about the distance of the strong force. We knew that it was around 1.5 times 10 to the negative 15th meters which is the size of a small nucleus. We knew that the strong force nucleons in a very large nucleus don't hold on to each other if they're on opposite ends and real far away from each other. So we knew the range of the strong force, and if we plug that in, c is just a constant, right? C is 3 times 10 to the 8th meters per second. So that allows us to predict the mass of this exchange particle, this meson. And if you plug that in and compute the numbers, you get a mass of about 130 MeV per c squared is the mass of the particle that is mediating the strong force. And it turns out that we later discovered this particle, and we call it the pi meson, or the pion for short, P-I-O-N. We use the symbol pi to designate the pion. And it actually comes in 3 different types. We have positively charged pions, we have negatively charged pions, and then we have neutral pions. It turns out that the masses of the positive and negative pions were about 140 MeV per c squared, approximately. And of the neutral pion, it was about 135 MeV per c squared. So we were able to predict the existence of these particles and even predict about how massive they were, and then later on we were able to find these, and so we said that the pion itself is what mediates the strong force. As I mentioned earlier, the photon mediates the electromagnetic force. And it turns out that the weak nuclear force is mediated by some other particles known as the W and Z bosons. These are actually all considered bosons, and those have been found in the lab as well. For the gravitational force, we think that there's an exchange particle for that as well, and we haven't found it yet, but we haven't had an experiment where we thought we could find it. The graviton is an elusive particle. And we did just recently find gravitational waves, so maybe, you know, within your lifetime we'll also discover the graviton and kind of complete this picture. Things have been updated with the pions, the mesons that mediate the strong nuclear force. I mentioned earlier that the protons and neutrons are actually made up of smaller things, and if you look at the force holding those smaller things together, we say that the exchange particle is known as a gluon. So these mesons are essentially a larger scale manifestation of what we call gluons. So here are all of what we call the 4 fundamental forces. All forces that you have ever encountered can be broken down to these fundamental forces. Usually it's the electromagnetic force. When you're pushing or pulling on something, it's the electrons repelling each other, as well as some degeneracy pressure, but that's a little complicated. Nuclear forces obviously just occur in the nucleus, and then gravitational force causes gravity. So these are responsible on the most fundamental level for all interactions between matter that we know of. Now maybe there's some other interactions with dark matter and stuff, yet to be seen. Go get a PhD in that and Nobel Prize or whatever, that'd be great. Here it's showing the relative strength of these different forces between 2 protons in a nucleus. So the strong nuclear force is the strongest, hence the name. Electromagnetic force is 100 times weaker. The weak nuclear force, this actually mediates nuclear decays. It's 1,000,000 times weaker. And then the gravitational force is so small it can basically be ignored in any nuclear considerations or particle physics analysis. It's just pretty meager and small. But it's important on large scales, you know, holds Earth together and the galaxy and all of those types of things. So let's look at that equation one more time. We had mc squared equals hc over 2 pi d. And now let's look at calculating the range of the weak force. If we know the mass of the particle, we can use that to calculate the range of the weak force, whereas in the other example, I didn't compute everything, but I kind of talked you through it. We found the mass from the range, so we can go the other way. Let's solve this equation for d, that's the range of the force, the distance that the exchange particle has to travel. So we get hc over 2 pi mc squared. Again, don't cancel out the c's here because it will come in handy to have that c squared there later. And for the weak force, the W and Z bosons, some of them are about 80 times 10 to the third MeV per c squared. Some are 90. So we're going to use the mass as, we're just going to take the average as 85 times 10 to the third MeV per c squared. So these are pretty massive particles, right? 10 to the third there. So if I go ahead and plug that into my equation here, now Planck's constant, that was 6.6 times 10 to the negative 34th. And I'm going to go ahead and include my units here, which I don't always do in calculations because I'm lazy. But it's going to be important to pay attention to them in this calculation. Alright, C, I'm going to actually plug that in because this one's not going to cancel out. So that's 3 times 10 to the 8th meters per second. Divided by 2 pi, that doesn't have units. I'm going to plug in this mass, so I've got 85 times 10 to the third MeV per c squared, and all of that's times c squared, so the c squareds go away, so that is nice. But I've got one other issue here. These seconds will cancel, but I've got joules over here. I want the meters to stay because I want a distance to come out. But I've got joules here and MeV. Those are both energy units, so if I do some unit conversions, I can get those guys to cancel out and just be left with the distance. So there's that conversion factor that I showed earlier on in this exciting film, which was 1.6 times 10 to the negative 13th joules per mega electron volt. Okay, so these will cancel, and then you got a joules left in the denominator in there. Anyway, crunch the numbers, and you get 2.3 times 10 to the negative 18th meters is the typical distance, the range over which the weak force can extend. So pretty short range. The last thing I wanted to talk about were antiparticles. So antiparticles were actually predicted before they were found by a guy named Paul Dirac, who was another pretty interesting physicist. And he predicted the positron. Now the positron is just a positively charged electron. And it's usually given the symbol E+. And it is the antiparticle of the electron. Antiparticles don't have negative mass or anything like that. They have the same mass as their regular particle friends, but they have the opposite charge. And the other thing is, if I collide a regular electron with a positron, then they do what we call annihilate each other, and then you just get pure energy out. No more mass, just photons. And all particles have antiparticles. So you've got a proton, which is positively charged. You also have an antiproton, which is negatively charged. A lot of times antiparticles have a bar over them to indicate that they are antimatter. So the antiproton has the same mass as a regular proton, but it's got a negative charge. And I know some people think, oh, antimatter is kind of theoretical or hypothetical, I guess is the better scientific word, right? But it's not. We've been creating antiparticles in labs for decades and know them really well. PET scans, if you've heard of, those use positrons, so they use antimatter. We know this stuff really well. We've actually got anti-hydrogen, where we've got a positron to orbit around an antiproton. There we go. So we've done some pretty amazing things. I don't know if we've done anti-helium yet, but maybe. Some particles are a little, well, you've got the neutron also has an anti-neutron, even though they're both neutral. If you collide them, they will annihilate each other and become energy, like all of these things would. Some particles are their own antiparticles. Photons, for instance, are their own antiparticles. So they don't have mass anyway, you collide them and they just stay pure energy, right? Okay, so that is the start of our wonderful adventure into elementary particles. See you next time.